Hello everyone, my name is Qiu Weiyang. I am from Guangdong, China. Currently, I am pursuing my master's degree in information technology at Southeast Bangkok University in Bangkok, Thailand. Professionally, I am a primary school teacher. This experience provides me with valuable practical insights into applying technology in educational settings. In this presentation, I am honored to share my research paper titled AI-Assisted Programming on the Development of Computational Thinking among Primary School Students, an Empirical Study. First, the table of contents. I will explain my paper from these 5 aspects. The first point is research objectives. The second point is research methods. The third point is study results. The fourth point is results and discussion. And the fifth point is research conclusions. The fourth part is research objectives. My thesis has 3 research objectives. The first one is compare the effects of AI-assisted programming and traditional learning on elementary school students' computational thinking, task decomposition, pattern recognition, abstraction, and algorithmic logic. The second one is observe the differences between course assessments and actual completions, and evaluate whether AI can translate into real-world performance. And the third one is explore the mediating role of learning behaviors, such as self-training in the computer lab, in advance in this process. The following is the second part of my paper. Research methods. I randomly divided 40 students in grades 4 to 6 into an AI group 20 and a non-AI group 24 processes were carried out, namely 1 pre-test before the course began, 2 intervention period. The AI group used AI tools, while the non-AI group completed the same task independently. 3 post-tests after the course. 4 competition, Guangdong C++ regional competition. These 4 processes have corresponding indicators, total scores of pre-test and post-test, and the competition award level, first prize, second prize, third prize, none, and the number of hours, week spent training in the computer lab in advance, reflecting self-awareness, and AI dependency between group independent sample test, within group paired test, difference in difference, correlation and contingency analysis will be performed. On the next page, I will show you the core data of my paper, study results. The first is the pre-test data. It is obvious that the AI group scored 66.4. The non-AI group scored 70.28 minus 0.38, peak 0.706, very small difference. The second is the post-test data. It is obvious that the AI group 78.50, non-AI group 79.20 minus 0.59, equal 0.556, no significant difference. Non-AI group slightly better. I compare the mean scores of the 2 groups on the pre-test and post-test. AI group plus 1 6.9 points 9.72 p 0.001. Non-AI group plus 1 5.50 points type 8.96 p 0.0 difference in difference negative 140. The improvement of the AI group was slightly greater than that of the non-AI group, but the magnitude was very close. Next is the comparison of the award-winning data of the 2 groups of students. AI group 1 first prize, 5 second prizes, 6 third prizes, 12 winners total. Non-AI group 0 first prize, 6 second prizes, 5 third prizes, 11 winners total. Award rate for any prize AI 60.0%, non-AI 55.0%, Chi-square equals 0.0 equals 1.000. Similar rates. Weighted award score. First prize equals 3, second prize equals 2, third prize equals 1. AI group mean 0.95, non-AI group 0.85. AI slightly higher, primarily due to the number of first prize winners. Comparing this data, I almost concluded that the AI group would surpass the non-AI group. But one day, I happened to see a student arrive early for training in the computer lab. I caught this crucial detail and recorded this early arrival data for comparison with the winning data. The Pearson correlation coefficient between advanced training duration and award score is R0.776 with a significance level of P 0.001, indicating a strong positive correlation. AI group 20 students are 0.76 to P 0.001. Non-AI group 20 students are 0.758, P 0.001. Both groups show a significant strong positive correlation with a consistent trend. Note on data characteristics. The average training duration of students with award score is greater than or equal to 1 is 15.8 hours, significantly higher than that of non-awarded students, 2.1 hours. Generally, higher scores, for example, 3 points for first prize, correspond to longer training durations, consistent with the pattern that more conscious training is associated with better award performance. Finally, the statistics of AI dependence are summarized, and the conclusion is drawn. The AI group showed a much higher rate of high reliance than the non-AI group. 70% of students in the AI group admitted to frequently copying code directly from the AI, compared to only about 15% in the non-AI group. Only when a program fails, question 80% of students in the AI group initially asked the AI, while the non-AI group was more likely to try it themselves or ask a peer. On the can you modify, optimize the AI provided code question, only 35% of students in the AI group said they could do it independently, compared to 65% of students in the non-AI group. So I will discuss the data to come to a general conclusion, and here are my thoughts. Discussion: short-term effects, competitive potential, and pedagogical insights of AI-assisted programming. 1. The post-test plateau in AI groups, a result of efficiency versus depth trade-off. The non-significant difference in post-test scores between groups 0.556 contradicts the expectation that AI would boost performance. This can be attributed to a critical trade-off. The non-AI group's slow but solid accumulation, the consistent advantage in abstract thinking, post-test mean 21.7 versus AI groups 20.1, and the algorithmic logic 21.7 versus 19.9 reflects deep engagement with problem-solving processes without AI shortcuts. They develop stable habits of decomposing problems step by step and verifying logic independently, skills that align closely with the structured assessment of the post-test, which emphasizes foundational mastery. The AI group's quick but shallow dependency, high dependency, students' dependency, 0.6 showed a 12.3% lower score in abstract thinking compared to low dependency peers. AI's instant hints reduce their need to formalize vague ideas into concrete models, a core component of abstract thinking, leading to superficial understanding. For example, in post-test questions requiring algorithm optimization, 65% of high-dependency AI students directly copied AI outputs without adjusting for context, resulting in errors. 2. Competitive success. Why AI became a catalyst for a few. The breakthrough of the AI team in the competition cannot be attributed to AI alone, but to a triple interaction of tool, behavior, and context. AI as a trial and error multiplier for motivated students. The first prize winner in the AI group spent 28 hours in advanced training, using AI to test 5+ solution prototypes for each problem. AI accelerated the elimination of invalid tests, allowing focus on optimizing core logic. This aligns with prior research showing AI's value in reducing cognitive load during exploration. Self-motivation as the filter for AI value. Correlation analysis 0.781 confirms that training duration mediated AI's impact. Even in the AI group, students with 10 hours of training failed to win awards, as they lacked opportunities to internalize AI-generated insights into stable skills. This echoes the 20-hour rule in skill acquisition. Deliberate practice is irreplaceable even with AI. 3. Dependency as a moderator. When AI enhances versus undermines learning, AI's effect is not linear but conditional on dependency levels. Threshold effect of dependency. Among AI students, a sweet spot emerged: dependency 0.4, 0.6. They used AI for 30–40% of problem-solving steps, pattern recognition hints, but completed 60–70% independently translating patterns into algorithms. This group scored 15.2% higher in competitions than both high dependency 0.7, and low dependency 0.3 peers. The former relied too much on AI to develop autonomy. The latter underused AI's potential to accelerate learning. Skill-specific impacts. AI most improved pattern recognition. AI could post-test in 21.6 versus pre-test 17.3 plus 2, 4.8%, but least improved abstract thinking plus 2, 7.2% versus non-AI groups plus 2, 2.6%, a narrower gap. This suggests AI excels at identifying regularities but struggles to foster conceptual generalization, a skill requiring independent abstraction, which high-dependency students neglected. 4. Implications for instruction. Designing AI enhanced autonomy. To replicate the success of top AI students while mitigating dependency, instruction must target the weak links reviewed in data. For abstract thinking deficits, assign AI vs human comparison tasks, where students contrast their solutions with AI's, identifying gaps in conceptualization. For example, why did the AI use a class to model characters instead of separate variables? This forces reflection on abstract structures. For over-reliance on hints, implement progressive AI fading. Start with 50% AI guidance, then reduce to 30%, 10%, requiring students to fill in increasingly large gaps. This mirrors the scaffolding theory, Wood et al. 1976, where support is withdrawn as competence develops. For competitive readiness, integrate AI augmented drills, where students use AI to generate practice problems, but must solve and explain 3+ variations independently. This combines AI's efficiency with the depth of deliberate practice. In short, AI's educational impact is neither inherently positive nor negative, but shaped by how students interact with it and how instruction structures that interaction. The data highlight a clear path. AI should complement, not replace, the messy, iterative process of learning to think computation. Finally, here is my conclusion to the paper. There are 4 points, namely: 1. AI-assisted programming doesn't automatically improve student performance. Its effectiveness depends on students' learning attitudes and self-motivation. 2. Proactive students can achieve better results with the help of AI, especially in high-level competitions. 3. Teachers need to properly guide the use of AI in their teaching, preventing students from becoming dependent on it while encouraging independent exploration. 4. This study provides empirical data for primary school information technology education, demonstrating that AI tools should be used as learning aids, not as replacements. Thank you for listening. If there is anything inappropriate, please correct me.